This video is about combustion analysis, which gives us yet one more way to use stoichiometry to solve a more complex problem. So what's combustion? It's burning something in oxygen. You can combust lots of things, but we're generally going to be talking about combustion of organic molecules that contain carbon, hydrogen, and or oxygen, because those two things, if you burn them, it produces just carbon dioxide and water. Okay, just those two things, no other products. So if we burn methane, we get carbon dioxide and water. We burn sugar, we get carbon dioxide and water. Okay, the balancing, of course, is going to be a little bit different, but we get carbon dioxide and water. Okay, so combustion analysis is therefore a way that we can use to determine the amount of carbon, hydrogen, and oxygen in some unknown organic compound. So this is going to allow us, this is one of the ways that you can determine that data that we've used to determine empirical formulas. So what we're going to do, we're going to burn a precise amount and collect all the CO2 and H2O, measure it. Generally, we would weigh it, get the masses of those things, and then use that to determine how much CH&O you had in the original compound. So I'm just going to go through a problem to show you how. So if we burn 18.8 grams of glucose in O2, we get 27.6 grams of CO2 and 11.3 grams of water. What's the empirical formula of glucose? You may already know this in this case because we have talked about it before, but we'll pretend that we don't, or we'll pretend it's an unknown compound, doesn't matter. So the first thing, there's a system to do this, okay? So the first thing to note is that all of the moles of carbon that were in the original glucose end up as carbon in CO2. So if we determine the moles of carbon in the CO2, we'll know the moles of carbon in the reactant. Okay, so we have 27.6 grams of CO2. Use stoichiometry to determine that we have 0.627 moles of carbon. Notice I have now gone all the way to carbon because there's 1 mole of carbon in every mole of CO2. So that's how many moles of carbon were in the original 18.8 grams of glucose. Step 2 is doing the same thing to determine the moles of hydrogen, which we can do by determining the moles of water, because again, all of the hydrogen that was in the original glucose will end up as the hydrogens in the water. Okay, so again, we just use our conversion factors to determine that. So we divide by the molar mass to find the moles of H2O, and then we want the moles of hydrogen, not the moles of H2O. This is one place people can trip up because there's, of course, 2 moles of hydrogen in every mole of water. So we have to multiply by 2. So we end up finding out there's 1.25 moles of hydrogen. Again, that's how much was in the original glucose. Then the third step is figuring out the moles of oxygen. Now this one is harder because there's oxygen in the glucose. There's also oxygen in the other reactant, the oxygen, okay, obviously. There's also oxygen in both CO2 and water, so we can't do the same thing for that. So how on earth are we going to figure out how many moles of oxygen were in the original glucose? This goes back to now knowing what a compound is made of. So the glucose is made of just carbon, hydrogen, and oxygen. So if we know how much of that mass came from carbon and hydrogen, which we can figure out, we know the rest must be oxygen. So we're actually going to determine the mass of the oxygen, not from the products, but actually from the reactants. So we can figure out how many grams of carbon were in that 0.627 moles. We can figure out how many grams of hydrogen were in that 1.25 moles. And if we know we had 18.8 grams total, so 18.8 grams minus 7.53 grams minus 1.26 grams tells us we must have had 10.01 grams of oxygen in the original glucose. We can now convert that to moles of oxygen, and we see that it's 0.626. At this point, now we are back to just our problems we've done before about determining an empirical formula. We know the moles of each of the elements in the compound. Okay, so we're just going to divide by the smallest whole number ratio. So these are our ratios right now. We have 0.627, 1.25, 0.628. Smallest whole number ratio will be found by dividing everything by 0.627. So we get that there's 1 mole of carbon, 2 moles of hydrogen, 1 mole of oxygen. So the empirical formula is C2H O. Okay? Glucose is actually 6 times that. It's C6H12O6. But remember, combustion analysis, determining empirical formulas, we have no way of knowing that. We would have to have more information, like the molar mass. So this is basically just another way to get started on an empirical formula calculation, another way to give you the data, but you do need to have a little bit of a sense of how to start, because a lot of the combustion analysis problems, I think if you've never seen one, it would be overwhelming to think about how can I possibly get there, okay? But it is pretty much the same system every time. And that's the end of this video.